Okay, so this is part 2 of chapter 6, and this has to do with kinetic energy and potential energy. In the last in the first part, we learned about work and power, and so on. So now we're going to look at the two mechanical energies, or two of the mechanical energies. Okay, first off, let's talk about kinetic energy. Kinetic energy is defined, is abbreviated K, capital K, and is defined as the energy that has the ability to do work. Kinetic energy requires work and returns work, and it's specifically defined as the energy of a moving object at a constant speed. So we have to put energy into an object to get it to move, and then when it's moving, we have to put energy into it in order to stop it, through the use of work. So we push on something, a force over a distance that does work and gives it energy, and then when it's moving, we apply force and over a distance, and that will take the energy away. The definition, the mathematical definition of kinetic energy is 1/2 mv squared. And so we're going to be, all we simply have to know is the mass of the object and how fast it's going, the speed, and then we can calculate that. The units for kinetic energy, it looks very strange, but if we take the 1/2 has no units, mass has a units of kilogram, velocity has a unit of meters per second, and then we square the meters and square the seconds. So technically this is the unit for kinetic energy, but if we split up the meters, so we have kilogram, meters over second squared, and then we separate the two meters, then we have kilogram meters per second squared, and that is a Newton. And so Newton meter is also a unit of kinetic energy. That has a special name called the joule, and that was named after James Prescott Joule in the mid-1800s. He didn't discover this or anything. He just worked a lot in physics at that time. So we're going to be doing some simple calculations for finding the kinetic energy. And so we'll do that right now. So here's an example. How much energy is required to get an electron moving with a speed of 1.90 times 10 to the 6 meters per second and a mass of 9.11 times 10 to the negative 31. So we're given the mass, we're given the velocity. We simply go ahead and plug that in to the kinetic energy equals 1/2 mv squared, right? So then go ahead and put the numbers in. Yes, the numbers are ugly because they're in scientific notation. We played around with that when we did universal gravitation. So just be careful about putting it in your calculator and such. So calculate that. Don't forget there's a square on this. So be sure when you put it in the calculator, you do a square on just the velocity. The result is 1.64 times 10 to the negative 18 joules. Now, you have no reference on that. What does that even mean to you? First off, it's an electron. It's very small, and it's going very fast. 1.9 million meters per second. Okay, so it has some kinetic energy. But what about a proton that has a mass of 6.67 times 10 to the negative 27? So the mass is larger. We're just going to say it's moving at 1.9 times 10 to the 6 meters per second also. So calculate that kinetic energy. We put the numbers in the formula. So we have 1/2 times 1.67 times 10 to the negative 27 kilograms, and 1.9 times 10 to the 6 meters per second squared. So what do you guess? Is it going to be more? And if it's going to be more, how much more? That's right. You should have got 3.01 times 10 to the negative 15 joules. And so you say to yourself, okay, maybe that's a lot, right? Well, these are 3 decimal places off of each other. So that would indicate that it's like 3 decimal places or 1,000. And because this is almost 3 times as much as that or so, it's actually 1,800 times more than the electron. Yeah, that's quite a bit. Now we're going to look at the work energy principle. The work energy principle says that the work done will change the kinetic energy. So sometimes it's going to be like this bus down here. This bus is moving along, and so it has its mass times its velocities, or one half times its mass times velocity. So it has a kinetic energy. Later on, it has more velocity, so it has more energy, and so this indicates that over this distance there must be some work that's being done. And so the overall work, or the net work, if you will, is equal to the change in the kinetic energy, which is the final kinetic energy minus the initial kinetic energy. So that's going to be equal to 1/2 mv squared, which is the final velocity, minus the initial velocity. Now, mind you, it's not v minus vo squared. It's the difference of the 2 squares. This is referred to as the work energy principle, which states that the net work done on an object is equal to change in the kinetic energy. We'll see how that plays out in some example problems, but what we will find is positive work is done on an object, it'll increase the kinetic energy, and when negative work is done on an object, then it'll decrease the energy. Okay, so let's take a look at the next type of energy, and that's potential energy. By definition, potential energy is the energy by virtue of external forces on it. So it could be energy gained by gravity. So we put a force on an object in a gravitational field, then we can increase the potential energy, or the work that we put in will be stored as potential energy. Or it could be elasticity, like a rubber band, or a bungee cord, or a spring, or something like that. There are other types of potential energy, and maybe we'll look at some of them in the future, but right now the mechanical energies we're going to look at are these two, the gravitational and the elasticity. The gravitational potential energy is abbreviated with a capital U, and it is work is required to lift an object. So we have this object in a gravity field, right? This is going up and down. So we have the weight is pushing down, the hand is pushing up. So this is an external force, and so it is changing. If the force is exerted over this distance, then it's going to increase the potential energy. So the work opposing gravity, which is force times distance, will actually equal mg times h. If we use the h as the height, I realize that h and that d are the same thing, but I tried to match the height that way, not the picture. This increases the potential energy since it is higher in the gravitational field. So because it's higher up, then it has more potential that's being stored. So the work done on an object will change the potential energy. Work is what translates to the ability to do work from that height. So if this was like a brick and it was up at this height and you dropped it, then it would do a certain amount of work on the thing that it dropped onto. The higher up it goes, then the more work it will do when it lands. So gravitational potential energy. All right, so we're going to calculate that basically this way. And so here's from your formula sheet. The change in gravitational potential energy is equal to mg delta y. So we'll focus in on that y because it's on your formula sheet. Mg, of course, is the weight in newtons, and delta y is, of course, the vertical distance relative to the base level. It doesn't matter about the path that it takes. So it could, if you pick up an object, you're going to measure the vertical distance that it goes to calculate this increase in potential energy. Okay, let's try an example. How much gravitational potential energy does a 64 kilogram pole vaulter gain if his center of mass rises 4 meters during a vault? So we are going to simply use the potential energy equals mgh, and that's going to be 64 times 9.8 times 4 for 2509. Pretty straightforward. No tricks, on this. It's just pretty straight. The next question is, how much does he lose if he once he reaches the ground? Ponder that for a second. Oh, that's true. It's going to be 2509 because he's going to lose all of it. The negative sign simply means that he's going to lose, there's going to be a loss of energy. Okay, so the next topic is on the total mechanical energy. What's been found is that the total mechanical energy stays constant for conservative forces. Now, think about what a conservative force would be. This would be a force that doesn't go away. So potential energy is conserved, kinetic energy is conserved, but friction, or the work done by friction, is not a conservative energy, is not a conservative force, so it doesn't stay constant. So if there is friction, then the conservation of mechanical energy is not valid. So we use a capital E to mean total mechanical energy. And that's going to stay constant. So it's always going to be the sum of the kinetic energy and the potential energy. And this is referred as the law of conservation of energy. Notice that there's no mention in here of friction. So this is going to be in frictionless situations. An object's energy is converted from one form to the other. So if we lift an object, it takes work to do that. We're increasing the potential energy. We then release the object. It then converts that to kinetic energy and loses the potential energy as it falls. So the work to lift an object increases potential, and then when it's released, it converts it back to kinetic energy. The law of conservation of energy is that the total energy is neither increased or decreased in any process, so it remains the same. Energy can be transferred from one to another, but the total energy remains the same. Dissipative forces like friction removes usable energy. So an example. Okay, so let's take a look at an example. We have this roller coaster. Has a mass of 200 kilograms at an amusement park. It's at rest at the top of a 30-meter hill from point A. So from 30 meters from some base level down here. It starts to roll and it reaches point B, that is 10 meters above the ground, and then it goes back to up to C, which is 20 meters above the ground. Assume no friction, and we're going to calculate how fast it's going when it's at point B. So we use the conservation of mechanical energy, which says the kinetic energy at the beginning plus the potential energy at the beginning equals the kinetic energy at B and plus the potential energy at B. Right, so we substitute formulas for that. The kinetic energy at the beginning is 0 because it is at rest. And then mass times gravity times the height at A, which will be 30, plus 1/2 mass times the velocity squared, and that's what we're going to be looking for, is the velocity of B, plus the mass times gravity times the height, which will be 10 that at point B. So we plug in the numbers, and we have 0 still hangs in there. So we have 200 times 9.8 times 30. That'll be the mgh at the beginning, equals 1/2 200 times velocity squared at B plus 200, 9.8 times 10. So do the, obviously you can see that 200 is a factor in all of those. So you could take those out, eliminate those. So we have 9.8 times 30, and we're going to subtract 9.8 times 10, and then we're going to divide it by 100. Go ahead and do that. So we essentially have the square root, so don't forget the square root of 2 times 9.8 times 30 minus 10, because all those 200s go away. And so that comes out to 19.8 meters per second. All right, so how fast is it going at C? Well, you could now take the velocity from B up to C, but you could also go all the way back to the beginning and then just do the same thing, but instead of 10 right there, you're going to put 20, because everything else will be the same, and this will be subscript C. So we could actually take it right from there, and the velocity at B will, that should say C should be 2 times 9.8 times the difference in that. So you should calculate that to 14 meters per second. Okay, so those are some examples for kinetic energy and potential energy. If you have any questions, contact me in the usual manner. Thanks for watching.